I remember January 2019. Do you remember January 2019? Oh, it was a simpler time. Something happened that month. A video came out on the internet. This video was called The Most Unexpected Answer, I'm looking it up, The Most Unexpected Answer to a Counting Puzzle. And this video is from one of my favorite YouTube channels, 3 Blue 1 Brown, where I learn a lot of wonderful math stuff and I get a lot of inspiration for stuff that I do. And what this video was about is it was about these two blocks. There was a small block and a big block. And these blocks, they moved around, they bounced into each other, they clacked. It was like the most beautiful clacking sound I've ever heard. And then they bounced into a wall. And after a while, just count up how many times they're bouncing into each other. And this weird thing happens. This number appears. This number, which is the digits of pi, appears based on how many times they're clacking into each other, which is crazy. Now, if you want to know why that occurs, you should go and watch the 3 Blue 1 Brown video series, and even towards the end of that 3-part series, 3 Blue 1 Brown makes a connection to optics, and there's so much beauty and wonder in there. This is not a new concept. You can find some other resources. There's a wonderful paper from 2003, I'm looking up the title of it now, by G. Galperin called Playing Pool with Pi, the number pi from a billiard point of view. There's a number file video, and I'll also link to some other resources where you can read about this particular phenomenon and why it occurs in this video's description. But that's not what I do on this channel. What I do on this channel is I code stuff. So I'm going to attempt in this coding challenge to make my own version of 3 Blue 1 Brown's collision clacking magic wonderful thing, and we're going to see, like, can I really make this happen just in the browser in JavaScript, and can I actually write some code that's accurate enough to get the digits of pi, and where does this all break down and what happens? So let's code. Now, to celebrate Pi Day, I'm going to do something a little bit different. I'm going to just start with a little bit of boilerplate code. I kind of use the same stuff in so many of my examples. Maybe I can save you 5 minutes here of me typing this part out. So what I'm starting with is just a very basic object-oriented system. I have a class called block, and each block has an X and a Y. That's where it is in the canvas. And it has a width. It's a square, so the width and the height are the same. And then when I want to draw it, I just draw it as an image, and I've loaded one of my coding train characters, the square character from the coding train. I also have in here a little clack sound loaded that I may or may not use. And then I have created just two blocks. Block 1 appears at 100 with a size of 20. Block 2 appears at 200 with a size of 150. And then I am showing both those blocks. All right, so what do I need to do? What I want to first do is give these blocks a velocity. So let me go into the block class and add a velocity. I'm going to call it v. And then I am also going to write a function called update, where I will say this dot x plus equal v. So the idea here is it has a velocity and x changes by that velocity. Then I'll go back to the sketch and let me give them a velocity like the block 1 is going to have a velocity of 0, and block 2 will have a velocity of -1. And then I should be able to say also here, I can just call update for both of them. Update, update. V is not defined. Did I really forget the this dot already so early in this challenge? I think that's what I did. I totally forgot the this dot. Oh, this dot, this dot. So now what I need to do is I need to figure out how do I check if the two blocks have knocked into each other. Okay, the way that I would do that, let's write a function. I like to do everything in the class when possible. I'm going to write a function called collide, and I'm checking if I'm colliding with another block, call it other. So I'm checking if this block is colliding with some other arbitrary block. So how do I know? If this is block 1 with an x and a width, and this is block 2 with an x and a width, I know that they are not intersecting if the left side of block 2 is greater than the right side of block 1, or if it was on the other side, right? If the left side of block 1 was greater than the right side of block 2. Otherwise, they must be intersecting each other. And this is a really simple situation. I don't need to check y's and heights because they're only moving along this one-dimensional horizontal space. By the way, the mass is going to be a key concept here. Don't worry, I'm getting to that. If you know that you're like, why you don't know the mass? Talk about the mass. So now I can say, I can look at basically say like if this dot x plus w, that's the right-hand side, is greater than other dot x, right? Oh no, is less than, right? Or if this x is greater than the others, x plus others dot w. And this has to be a this dot. All right? So now I'm going to say print line, oh no, print collide, not collide. Not collide. Otherwise, print collide. Let's see if I got this right. So it's moving, it's moving, it's moving. Oh, I got to call this function. That would be nice. So I'm going to say block one dot collide, block 2. So I'm adding that in, and it's moving, not collide, not collide, not collide, not collide, not collide, not collide. It's going to collide. It's colliding, it's colliding, it's colliding. Eventually it's going to get to the other side, go to the other side, get to the other side, not colliding anymore. Okay, my algorithm was correct. So really, if I want that to just return true or false. So what I'm going to do is I'm actually going to say, I could write return false here, but another way I could do this is just say return not this expression. This is a test to see if those two blocks are colliding with each other. Whew. All right, if block 1 collides with block 2, now what I want to say is block 1 bounce block 2. All right, I want them to bounce off of each other. So certainly at some point we're going to have to deal with the fact that there's a wall here. But right now I'm just looking at these two, and what I want to do is I want to calculate the new velocities for a perfectly elastic collision. So this has a velocity, this presumably also has a velocity, maybe it's moving that way, maybe it's that way, maybe it's at rest. And I need to, in an elastic collision, there's no friction, there's nothing else here in this environment, they're not like squishy things, no momentum, no energy, nothing is lost. So I need the formula for an elastic collision. Luckily, I have that open right over here. And you can see this is a formula that's following both the conservation of momentum and the conservation of kinetic energy. So with both of these formulas from physics, we can then get the new velocity, right? U here is the old velocity, and V is the new velocity. So the new velocity is a function of the both objects' mass and their previous velocity. Let's first add the idea of mass. So I'm going to go in here and I'm going to add the idea of mass. And first I'm just going to say, hey, the mass is 1. So let's not worry about mass right now. By the way, what happens if the mass is 1? Think about this. If they're equal mass, if they're both equal mass and this one is stationary and this one's moving and they clack, right? All of the momentum and energy is transferred. This one stops, this one moves. But that's not what's going to happen when the masses of each are different. So that's when it's going to get really interesting. Okay, so now we want a function called bounce, and I'm also going to say other. And it would be really nice if I could just have that formula right over there for me to refer to. All right, so I took a screenshot of the formula, so I've got it over there to refer to, and I just need to implement it here in this bounce function. So 1 is this. 2 is other. So I'm writing it, I'm not referring to my blocks as block 1 and block 2. I'm referring to it within the object as this and other. So what I want to do is say this dot v, but I don't want to start messing with v because the old value of v is part of the formula. So let's do this. Const v, actually, you know what? Let new v equal this dot m minus other dot m divided by what? Let's make a variable called sum of m, which is this dot m plus other dot m. So this is divided by sum of m, and then times this dot v, right? So that's this side. And then, I mean, I could do this in one line, but I'm running out of space here. So then plus equals 2 times other dot m divided by sum m times other dot v. So I think what might make sense here is, the thing is, I don't want to update this object's velocity. I guess I could do both of them. I'll just do both of them in this function. I was thinking I could return it, and then, because it's the same formula both ways, I'd rather not duplicate my code. Let's try it this way. I'm going to return new v. You can see how this is the same formula twice. It's just written in reverse order for v2. But if I change the 2 there and I'll change all the 2's to 1's, we'll get the same thing. So I should be able to say, if I go back into sketch.js and I say, I'm going to say v1 equals block 1 bounce block 2. I'm going to say v2 equals block 2 bounce b1 block 1. And then I should say, I'm going to update their velocities. This I don't know if I love, but this will work. So let's see what we got here. Come on, clickety-clack. Go, bounce that thing. Look at that. They're the same mass. So, and by the way, it was like moving, it's like a funeral dirge over here, the way that thing's moving. Let's give it a bit of a faster velocity to start. And we can see, boom. That's a perfect elastic collision. Now, it doesn't look very realistic because really what we're seeing here is should look like this, right? That's what we want. If both of those objects have the same exact mass, one's going to transfer all of its energy and momentum to the other one. Now, what if they have different mass? So let's give this one a size of 20 and this one a size of 200. And actually, I'm also going to give them each individual masses. So this will have a mass of 1, and this one's going to have a mass of 100. So it's not perfect, and some weird stuff is happening because I'm introducing another argument here. So now let's see what happens. Oh, there we go. That's what we want. Look at this. Right? Now, the formula is working with different masses. All right. Oh, we're doing well. Oh, we need a wall. Right? We need for the little block to hit the edge. So the wall is another thing that doesn't exist in the real world. We're looking at a perfectly elastic collision with an immovable fixed static wall. In other words, a wall, a block of infinite mass. So we can think of this wall as having infinite mass, but honestly, the easiest way to do this is just, if it hits the wall, just reverse its velocity. That will simulate a perfectly elastic collision with an object of infinite mass. So I'm going to write a function like hit wall. If this dot x is less than 0, then this dot v times equal -1. And then I only need to, in this case, I only ever need to check block 1. So now I'm going to check block 1, hit wall, and let's go here. Boom, 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 boom. Amazingly, that kind of sort of did something. Now, are we getting the right numbers? This is the question. And also, I kind of want to hear that clack. Don't you want to hear that clack? So let's add the clack. Oh, I just realized this way that I did that, I really should have this also be if block hit wall, then do something like block 1. Let's let these be separate functions, reverse, because I'm going to need to do counting. There's a bunch of things that are going to need to happen. So it's good for me to actually do it this way. Return, I'm going to say reverse, and then, okay, so this looks right. Let me make sure this is the same thing. Oops, I hit refresh. Sorry. All right, let's see. All right, so that did something. Now, let's add the clack. I mean, we're really just here for the clack. The clack in the 3 blue 1 brown video is the most beautiful clack ever. So I think if I say clack.play, let's see what happens. Ooh. Oh, that's kind of good. I need to clack when it hits the wall, though, too. Oh, the clacking. Oh. It's a little weird how I like the clacking so much, is it? I don't know. It's very satisfying. All right, so now let's count. I mean, in theory, we're done. I have a feeling we're going to run into some big problems. But let's say int, so I'm going to start with a count of 0. I am going to create a DOM element. I'll call it count div, because I'm going to make a count div equals create div with the count in it. And then I am going to say count div HTML count, and we will increase the count every time something collides. Whoops. Line 6, error. Oh no, int. What am I doing? Int. Int. Oh, I feel like I'm in processing. It's a let. Let's make them the same mass. Oh, and I got to make this bigger. Yes. Okay. And then let's number format this. So, okay. Hey, that's kind of like pi, 3. Now, I'm going to make, okay, so here's the thing. The magic number here is 100. So if the mass of one of the objects is 1, the mass of block 1 is 1. The mass of block 2 should be the mass of block 1 times 100 to the power of something. So, and the 1 here this doesn't matter because this is just 1. The ratio, so I could do 100 to the first power, right? 100 to the 0 power, which would be their equal. 100 to 1, which would be 1. 100 to the second power, which would make this 10,000, right? To the third power. You see where we're going here. So what I want to do is, that's how I'm going to calculate the mass. So I guess what I want to say is, if the digits are 0, then this is M2. I'm going to say const M2 equals power, 100 to the number of digits. So that's 1 digit, and now that's 0 digits really, because I'm confused when I'm talking about digits, right? What I mean by 0 is the number of digits after the dot. Pi is 3 point what? Okay, now let's have 1 digit after the dot. 3.1, that's crazy. All right, here we go, 2 digits. Wait, hold on a second. Actually, the way that this would make the most sense is for, if I want to get 2 digits, I should be saying 100 to the power of 1, which is digits minus 1. And then this makes sense down here. This is not digits plus 1. And there we go. This is 2 digits. I should get the number 31. Okay, that's good. And then if I change this to 1 digit, I get the number 3. And by the way, when do I decide when to stop counting? So at a certain point, the second block, or I don't know which block is the first, which block is the second, is going to just go off and running forever, and they're not going to have another chance to ever collide. So I'm just doing that visually right now. But we could actually put something in here to determine when it's finished. But you can see here, now, even though they're both moving in the direction that way, but the larger block is moving faster, so they're never going to collide again. And that's something I could create a conditional to test for. But let's talk about the real problem here. The real problem is Euler integration. The real problem is the phony baloney physics simulation that I'm doing here. I am taking a giant step in time forward each frame of animation. And so the block is like moving, then it's covering, then it's colliding again. Everything is wildly inaccurate. So there are a variety of techniques of making a simulation more accurate. This diagram over here is illustrating this concept. So if the blue line is like the real thing that would happen in the real world with continuous time, if I'm just making guesses every so often, you can, with the red line, with the Euler integration, just adding the velocity with large time steps, you can see how the thing gets out of place. And this, if you were programming a simulation to try to get a rocket to land on some moon planet thing, you're going to have a problem with Euler integration. So there are a variety of techniques that are different types of integration techniques for physics engines. And then, of course, 3 Blue, 1 Brown talks about other ways to calculate the number of collisions that would happen based on thinking about the space in a different way. But what I'm going to do here is just see, what if I just make those time steps smaller? So in other words, if I recreate that diagram like this, and this is, with large time steps, well, if I could get smaller time steps, I could stay closer to what it really would be. So a way of doing that might be the following. I am going to create a variable. I'm going to call it time steps. And I'm going to put the digits at 1, just so we know it's always going to work. And I'm going to say the time steps, I'm going to just try, let's add 10 extra time steps. We can make this a constant. So there's always going to be, every time through draw, I want to do this 10 times. So I'm going to say, for let I equal 0, I is less than the number of time steps, I plus plus. And I'm just going to do this, all of this 10 times, right? All of this, by that I mean check the collisions, bounce the blocks, play the sound. Let's comment out the sound for a second. We'll have to think of a different way of dealing with that. Update the blocks. I'm only need to show once through draw. So if I'm doing that 10 times, the other thing I can do here is I can divide the velocity that I want to start with the number of time steps. So it's as if I'm doing the same thing, but with a tinier velocity, and I just do it multiple times through draw, so our animation happens faster. Let's see if this allows us to do, let's just check to make sure this is still working. 1, 2, 3. Oh, I missed the clack. I really missed the clacking. Let's try 2 digits. 1, 2, 3, 4, 5, 31. All right, that's pretty good. Now let's try 3 digits. And let's see. Should get 314. Come on. Go back. Hit the wall again. Hit the wall again. Clack. 314. Woo. Let's add the clack back in. What happens if I add the sound back in? That was tolerable. All right, 314. Okay. Let's try 4 digits. Uh-oh. Goodbye. So that didn't work. What if we have 100 time steps? Okay, that was, it worked though. All right, I got to deal with the sound. All right, so I think basically what we should do with the sound is I'm just going to say, let clack sound. I'm just going to assume it's not clacking. And then if it clacks once, if it hits anything, I will say clack sound equal true. Like only if it collides either with the wall or the other block. I'm going to play, and then I'm guaranteeing now that I can only, I will only play the sound once every time through draw. So this should really help things. So let's try this now. 100 time steps, 4 digits. 3.141. We're doing really well here. Okay, now 5 digits? How about 1,000 time steps? Looks pretty good. 6 digits? 10,000 time steps? That's pi, right? Go, clack! 3.14159. All right, save. I'm saving. 7 digits? 100,000? What? That seriously worked? That's pi, right? I got 7 digits just through this method? I really didn't think I was going to get that high. All right, let's try 8. Let's try like 500,000. What? Is it a 6 there in pi? I mean, could I really get 1 million? Wow, I'm surprised that it actually will go with 1 million. 9? But I don't think that it can handle 10 million. 10 million time steps each time through draw? Can I get away with like 5 million? What? 1.4, what's pi? 14159,265. That's right, that's pi. Can I really do 10 million time steps? I didn't think JavaScript. Okay, the other thing I should do here is I should constrain where it's being drawn. You can hear the frame rate is getting really, really low. So I'm just going to give these a variable called x constraint. I want to say block 1 can't be drawn any further than 0, and block 2, if this size is 20, can't be drawn any further than 20. And where I'm drawing it, let me say constant x equals constrain this dot x between this dot x constraint and I don't know, The width of the window should be fine. And then I'm going to draw it at X constraint. This will just visually, I think, make it look more correct. Oh, when an X constraint is not defined, because I probably forgot that this dot. Yes, I forgot that this dot. Oh, oops. No, I want to draw at the X that's constrained. I don't know what I'm doing here. Put this here, and now let's watch. It's counting. A lot of collisions. All right. Can we get to 10 digits? Let's try like 500 bazillion. It's just running really slow. There's too many time steps. But I think we probably will get the right number. It's the Pi song. We're counting the collisions on the Pi song. We're counting the collisions on the Pi song. Pi song, Pi song, Pi song. I don't have the digits of pi memorized. Whoa, hold on! We got 10 digits, everybody! Woohoo! Only 500 million, no, 50 million time steps. I had to look at this very close up. 50 million time steps per time through draw. I mean, why not, right? Oh, this goes to 11. We have to go to 11. Let's just add another 0 because why not? Loading, loading. Okay. All right, so I might need to speed this up, but I'll at least play you a little song. Three point 14159 265 3589 7932 3846 2 264 3832 795 884 1971 939 375 105 8209 7494 4592 Ah, whoa. Oh, yes. Oh, it's moving. It's moving. Okay. 3, 1, 4, 1, 5, 9, 2, 6, 5, 3. Okay, it's got to hit one more time. Go catch up, little guy. Catch up, little square, little one. You can do it. Give me a clack. You can do it. 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 Yes. 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5. That's 11 digits of pi in JavaScript V5 in the V5 web editor just by elastic collisions of 2 squares. Whew, what a coding challenge. All right, thank you for watching this coding challenge. This actually did happen during a live stream. Every once in a while I do live streams for YouTube members and patrons, and I just happened to be doing this during one of those. But this was so sort of fun and weird that I will include a link to that unlisted live stream if you want to take a look and see the long version of all of the time spent actually doing this coding challenge and waiting and waiting and waiting. I also have made a processing version of this. I've made some other attempts, some of them rather comical. For example, I tried to say, well, could Box2D actually do a good job of figuring out the elastic collisions more accurately? As you can see, that did not work. I also tried using big decimal. Now, in JavaScript, I'm using floating point numbers, and a floating point number just has 32 bits of memory to store. It's really just about 7 digits, I think. You could, in processing, I could use a double, which has 64 bits of memory to store the decimal number, but there are lots of implementations, big decimal being one in Java for storing huge decimal numbers with really high precision. And I believe there are some JavaScript analogs to that. So I will include links to all of that stuff in the code that goes along with this. If you could come up with a creative way of visualizing this, of optimizing it to make it run, you should definitely check out 3Blue1Brown's video. I have a version where I implemented the optics method, but I had to load the number pi in order to then calculate. So this is a question I'm asking you, the audience. Is there a way to count the number of collisions either without tiny, tiny time steps that take forever, or by having access to the number pi in the first place? I would love to know your answer or thoughts on that. Go to thecodingtrain.com, link in the description to this challenge page, and you can submit your own version of it there. Thanks for watching, and I'll see you before next year on Pi Day, hopefully. I mean, there's like Tau Day, it's coming up. Summer is right around the corner. June is busting out all over. Goodbye, see you later. 3.1415 92653 8979323846. It's Pi Day, Pi Day. Gotta calculate on Pi Day. Everyone's looking forward to the digits. It's Pi Day, Pi Day. Gotta calculate on Pi Day. Everyone's looking forward to the digits. The digits. Party and party, yeah. Party and party, yeah. Fun, 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 fun. Pi Day.